Okay, guys, good evening. And today we're going to talk about visual recognition, including some typical recognition tasks and a comparison of between a look back to classical statistical learning methods, as well as the training of statistical learning method, a typical training pipeline for machine learning models. And then we'll talk about the basic knowledge of deep learning, including the multi-layer neural network and how to train a multi-layer neural network. So maybe some of you have already been familiar with the deep learning concepts. Okay, so you can take this as an opportunity to review those concepts, and hopefully you will get some new insights. Okay, now let's start from visual recognition task. So first question, image recognition. Does it mean image classification? Are they equivalent? Image recognition and classification. So what is image classification? Given an image, and you assign a class label to that image. Well, you can assign in image classification. Normally, you assign one label to one image. But you know, since a picture is more than 1,000 words, so a picture is usually, an image is usually associated with multiple labels. Okay, so in image tagging, in your image database, one image can be associated with multiple labels. But regarding image classification, in standard image classification, one image corresponds to one category. But in multi-label image classification, one image can be assigned to multiple classes. Okay, for example, in tagging, image tagging, you can assign multiple labels to one image. Okay, so image classification or tagging, the two words that are often used interchangeably, and whether it refers to single class classification or multi-class classification, it depends on the context of your problem. Okay, now back to our question. Does image recognition refer to classification only? Well, the answer is not. The answer is no, because recognition, image recognition is a much broader term. It includes, can you name a few other tasks? A few tasks other than image classification. So when we say recognition, what can you think of? We want to recognize what? The objects within an image. We want to be able to understand the content of the image. Okay, so besides classification, image recognition tasks also include, for example, object detection. Okay, so object detection includes the localization. So what do we mean by localization? Localization is to place a bounding box, localize the object, locate the position of the object by placing a bounding box around the object. Okay, so object detection include localization, and what? What is the other task? What is the other task in object detection? Classification, right? So in addition to locate the object, we also want to understand, we also want to identify the category or the classes of the object. Okay, so another typical recognition task is object detection. Can you name another task? Typical task in CV. For example, the segment anything. Have you heard of that? Segment anything tool developed by Meta. It's called segment anything model. So these are the segmentation results obtained by this model. You can just search for this model on Google, and you will I believe it's now version 2 or version 3. So you can see well, this model, it divides the image into different regions where each region corresponds to an object. Okay, for example, this is this is car. The result is very impressive. Segment anything. So where each object is a ball. So segmentation or semantic segmentation is this one. Semantic segmentation is another typical or basic task in computer vision. So it involves dividing image into different regions, or equivalently grouping pixels into a class. For example, these pixels are the pixels within this region. They are grouped into a class called sky, the sky class. And similarly, these pixels within this region are assigned to the mountain class. Okay. So segmentation can be considered as a grouping or clustering task, because it involves the grouping pixels into different clusters, right? But it can also be considered as a classification task at the pixel level. Why is that? Because essentially we are performing classification for every single pixel within the image. You know, for the before the deep learning era, the most popular approaches used for segmentation is normalized cut. Normalized class. We will briefly talk about that later. It is a grouping or clustering algorithm. Clustering algorithm. Okay, so we are given this image consisting of 400 times 300 pixels, which is equivalent to this many pixels. We can build a graph to grouping all those pixels into different clusters. Okay, so this is like the normalized class is like one of the most popular approaches for segmentation. But now within when we enter into the deep learning era, we train a segmentation model end to end using a deep learning a CNN network. Okay, and when we train the model, we need training data like this. So how we construct the training data? If we want to train a segmentation model, this is what you have. This is like the ground truth, for the input image. Okay, so within the ground truth image, every single pixel is associated with a label indicated by its color. So every pixel in the background here is assigned to, for example, the grass, the category of grass, or the background class, the grass, for example. Okay, and every single pixel within the human is assigned the person class, and every single pixel for all the shapes are assigned the shape category, and all the pixels belong to the dog. They are assigned the dog category. So this is the ground truth image. Okay. So when you want to train a segmentation model end to end, this is what you need to create such training pair. Input image, and the ground truth results, segmentation results. Okay, and then you can train a CNN network end to end using paired training data. So one thing you need to keep in mind is that when we train the network, this is the ground truth. So the ground truth, we want to train a network that is able to classify each pixel, within the image. Okay, so from this perspective, semantic segmentation can be considered as a classification task at the pixel level. Okay, so previously we say when we do image classification, we assign a category or a class label to the entire image. Okay, but for semantic segmentation, we assign a class label or a category to every single pixel within the image. So that's why we say semantic segmentation is a classification task at the pixel level. Okay, then what's the difference between semantic segmentation and instance segmentation? Well, it's pretty obvious from the figure. So in semantic segmentation, it doesn't distinguish between individual objects. Okay, it doesn't distinguish the 5 sheep within the image. It doesn't distinguish individual objects because the 5 sheep, they all belong to the sheep category. But the instance segmentation requires the differentiation between individual objects. So in instance segmentation, in addition to assign a class to each pixel, for instance segmentation, in addition to classify all these sheeps, in addition to recognize these sheeps as the sheep class, we also need to assign individual ID to each sheep. For example, sheep 1, sheep 2, sheep 3, sheep 4, and sheep 5. Okay, so we need to assign a unique ID to distinct object. We need to put a mask on the to differentiate different objects, different individual objects. Okay, so that's the key difference between semantic segmentation and the instance segmentation. Okay, well, instance segmentation requires the differentiation between individual objects. Okay, for detection task, it involves the placement of bounding box. And as you can see, the bounding boxes come with different colors, indicating the categories of the corresponding objects. Okay, so so visual recognition is a much broader term than classification. It involves object detection, segmentation, and semantic segmentation. These are the perhaps the 3 most popular tasks, fundamental tasks in computer vision. Then what about activity recognition? Activity recognition, this task is closely related to image description or image captioning. It's about understanding the content of the image. Image description, image captioning. What's the difference between image captioning and description? Well, image captioning refers to the generation of a brief description, brief description about the image. Okay, and as you can see, we have a long description, a pretty detailed description about this image, and this task is called image description. But if you only extract, for example, the first sentence, a busy street in an Asian city. Okay, if you only use a few words like this. It's called captioning. So captioning means using a few words or given a brief description about the image content, while image description involves much more detailed description of the image content. So that's the key difference. Okay, so in object detection, we find, for example, find the pedestrians. In activity recognition, we may, we first locate the persons, and then we can classify their activities based on the features or contents within the bounding box. So to summarize, image recognition involves a wide range of computer vision tasks. And in the following, in a few weeks, we're going to talk about how to apply deep learning algorithms for object detection, segmentation, and instance segmentation. Okay, now before diving into deep learning or deep recognition pipeline, let's first review the classical statistical learning pipeline, which is referring to shallow recognition pipeline, and some basics like how to train a machine learning model. Okay, now taking image classification as an example, because it's very simple. The statistical learning framework aims to learn a function or a classifier F to classify the input image into different categories, predefined categories. Well, in the deep learning pipeline, the function F are what? In deep learning pipeline, the function F can be a CNN network, right? It could also be a transformer, visual transformer, VIT. Okay, but let's start from some simple classifiers. Well, these are the classical statistical learning methods or tools or classifiers before the deep learning era. And the support vector machines are among all those classifiers. The support vector machines are the most popular one. You can see there's a plot. This, okay, and you can see, well, this is deep learning. The blue curve represent interest in deep learning, and the red curve represent interest in support vector machine. What can you see? What can you observe on this graph? Interest over time. So at this point, at the beginning of 21st century, which I believe most of you were born around this time. And around that time, you can see SVM is the highly preferred model compared to deep learning. So no one used neural network around that time because they just don't work. They didn't work. Okay, so as we come to 2012, this is the turning point. That's a turning point. There's a signature event called RLESNet. RLESNet. Okay, so RLESNet won the ImageNet competition, ImageNet challenging that year. So it outperformed every other method, the RLESNet. It outperformed every statistical learning method, every other method. And it won the competition, and it achieves, I believe the accuracy is around 80, 84 or something. So far more effective than previous methods. And starting from 2012, you can see there's a growing interest, a booming interest in deep learning. Okay, until now. Okay, so why support vector machine was so popular like 20 years ago or 10 even 10 years ago or 15 years ago, I would say. Okay, so let's find out. Okay, so in classical statistical learning pipeline, it involves two stages. So one is to well, this is a classical recognition pipeline. In classical recognition pipeline, it involves two stages. The first one is to extract features. And the second one is based on the extracted features, train a classifier using some off-the-shelf classifier, like, for example, the simplest one, the nearest neighbor, or SVM. Okay, so this is the classic or classical recognition pipeline. Very simple. Okay, so step one, during training, given training images, what should we do? We extract image features. So can you think of some methods for image feature extraction? So we have talked about for example, the SIFT descriptor, extracting the key points. So that method can also be used for feature extraction, right? Because we extract some key points from the image, and we can use those key points to represent the image. Okay, and there are also there are other methods like GIST, like a few methods similar to SIFT. They run some detection algorithm, like SIFT detector, and then they extract some key points, and each key point is represented using a vector. And these vectors can be combined to represent the image. Well, a typical representation method is called the bag of words feature representation method, which we will briefly introduce later. Okay, now back to our statistical learning framework. Well, during training, we are given a set of training data with ground truth. Okay, so typically we represent label examples, training samples using X and Y pair. Using X and Y pair, where X is usually represent input feature. Input, you can think of X as the image or or its features. Okay, X. And Y is the label or the output of the prediction. Okay, so we will follow this notation using the standard notation using XY pair to represent input and output. Okay, during training, during the training process, the first step is to extract image features, followed by training a classifier or a learning model. And during the testing phase, we apply the trained model to the learned model, the trained model, to make prediction on unseen samples. What are unseen samples? On the images or samples that do not appear in the training data. Okay, so in the statistical learning framework, we want to train a model such that this model, we want to train a model that perform well, which is robust on testing examples, on new unseen test examples. And this ability is called generalization. Okay, generalization ability. Okay, so we want the model to generalize well on new samples. And this ability lies in the at the core of machine learning. You know, the large language models. The large language models have strong generalization ability. So it can basically answer any questions you ask. It has very strong zero-shot learning capability. Okay. Anyway, so this is the core concept, generalization in machine learning. So the idea is that we want the model, not only the trained model, not only the model can perform well on training data, because training data is contain only a small subset of the images. Okay, so we want to train a model. It can perform well on numerous new images unseen during training. Okay. Okay. So for statistical learning pipeline, stage 1, feature representation. As we mentioned earlier, for this step, you can apply SIFT descriptor or shift detector or gist or many other options. And for trainable classifiers, can you name a few? It can be, well, the simplest one, the k nearest neighbors. This is the simplest classifier everybody knows. What else? Decision trees, right? As well as support vector machine linear classifier or kernel SVM. Kernel SVM makes linear, or any other classifier, naive Bayesian, logistic regression, PCA, etc., etc. Okay. So in the statistical learning pipeline, feature representation is critical. Is critical because the classifier are simple classifiers. Okay, simple classifiers. The classifier we apply typically involve k nearest neighbor SVM, and they are simple classifiers. So feature representation is critical. Comparing the classical recognition pipeline with the deep recognition pipeline, what can you observe? As we mentioned, for shallow pipeline, for the classic pipeline, the trainable classifiers like XVM, decision tree, well, they are simple classifiers. But in deep learning pipelines, we also use simple classifiers. Well, for example, the last few layer of CNN network is the multi-layer perceptron, or FCN, fully connected network. Okay, it's just two fully connected layer, two fully connected network, two layers of MLP. Well, you may say these fully connected networks, well, it involve many neurons and many weight parameters. So you can say the MLP is a simple classifier, but well, it's architecturally simple. Okay, only two layers. Well, I want you to appreciate the difference between the shallow recognition pipeline and the deep learning pipeline. What are their key differences? Well, in the shallow recognition pipeline, the two steps are separated. They are independent. Clear? So in shallow recognition pipeline, usually we extract features, and then we use those features to train a classifier. The two stages, they have minimal interaction. But in the deep recognition pipeline, the feature extraction layer, the convolutional layers, and the MLP, they are connected. They are trained together simultaneously. Okay, so they are trained jointly. So that's one key difference. The deep recognition pipeline, in deep recognition pipeline, the classifiers is trained jointly with the feature extraction layers. Whereas in the shallow recognition pipeline, the feature extraction stage is independent from the training of the classifier. Okay. Another key difference is that is the difference between deep and shallow. Okay, so in the shallow pipeline, feature representation is usually obtained by one step. For example, running the SIFT detector. Whereas in the deep recognition pipeline, we extract features using multiple layers. So we do not just learn features by one step. Instead, we learn a feature hierarchy from pixels to classifiers. Okay, so in the deep recognition pipeline, given an input image, the output is just a few category. The output is a vector whose dimension is equal to the number of categories. Okay, and we extract the features. We using using multiple layers, and we reduce the feature map, the dimension of the features gradually. Okay, gradually using modules like pooling layers and convolutional layers. So we reduce the feature dimension gradually, and during this process, we learn a feature hierarchy. Okay. So what do we mean by feature hierarchy? Okay, so these are low-level features and mid-level features and high-level features. Okay, we learn a high-level concepts, and low-level representation. Okay, we learn a feature hierarchy. So that's the key difference between shallow pipeline and deep recognition pipeline. Okay. Now let's spend a few minutes to talk about a typical feature representation method for the shallow pipeline. Like we said, given an input image, we extract a few key points from the image. And each key point is represented by a feature vector. Okay? For example, we extract a few patches from this image. Okay, and these are the patches. These are the image patches extracted from a set of training data. And each patch is represented by a vector. Well, here for illustration purpose, we only consider 3D vectors. Okay, so we extract many patches from images within a training set. And each patch is represented as an high dimensional point, high dimensional vector. Okay? And then we group these image patches, or we group these vectors into different clusters. We group these vectors into different clusters, and each cluster is considered as a visual word. Okay, so this is a visual word. This category, this is a cluster. This cluster is a visual word. Because it represent maybe it represent a significant feature within the data set, from the data set. Okay. For example, these are the given these images from the data set, we extract the patches from the images. Okay. These are the patches from the images. And then we group these patches into different clusters. And as you can see, each cluster, this cluster is composed of these image patches because they have similar appearance. Okay. And this cluster is composed of these images because they all have similar appearance. Okay. And their average is considered a visual word. For example, this is the visual word for the visual word for the wheel, for the lower half wheel of the cars. Okay. And this one I'm not sure. So each visual word here correspond to each visual word here correspond to a representative part of the car. Okay. Okay. And then we can represent an image using those feature words. You know, given an image, we extract some patches, and then we see each patch. We look at the relationship between the extracted patches with the visual words. Okay, so here is an example. First of all, we learn a visual vocabulary like this. The visual vocabulary in this example, the visual vocabulary involve four patches. Four patches. The this is the bike, some part of bike, and some part of the face, some parts of the face, and some part of the violin. So there are four visual words in the vocabulary. In the car example, we have like a dozen of visual words, well, as shown on the image. Okay, so first of all, we construct a vocabulary. We construct a vocabulary using training images. Okay, and then given a test example or given a training example, we quantify their features using visual vocabulary. What does it mean? Given the visual vocabulary, see, these are the visual vocabulary. We assign the image patches extracted from this image. For example, we extract six patches from this image. And then we calculate the distance between these image patches and the visual vocabularies. Okay, and we assign each image patch to its closest center, to its closest visual word. Okay, as you can see, these image patches are assigned to the two visual words because they are similar. They are most similar to the two visual words. Okay, while for the bike image, they are mostly assigned to the bike visual word, the first visual word. And for the violin images, these patches are assigned to the column correspond to the violin visual word. Okay? And then we can represent images using the histogram. This is a histogram. Okay. So it's called bag of words features. Bag of words features. So first of all, we need to construct a vocabulary, visual vocabulary, where each visual word represent a signature feature, represent a significant feature within the data set, from the data set. Okay? And then we can represent our image. We can represent each image using those vocabularies. So we represent different images using the same vocabularies. And we finally, we use the histogram to represent their features. So this is the bag of words feature representation, which is the very popular approach used in 12 years ago. Okay, now let's take a 10 minutes break. Okay, so we have already introduced the bag of words features for the first stage of the classic recognition pipeline. Now let's introduce the second stage, the trainable classifiers. Specifically, we will talk about the nearest neighbor classifier. And we'll briefly introduce the linear classifier because it's closely related to the perception algorithm, which are the building blocks. The building block of what? Neural networks. Okay. Now let's start from nearest neighbor classifier. So the nearest neighbor classifier is the simplest, perhaps the most simple classifier. So given a text example indicated the green text example, and with some training examples from blue training data and the red one. Okay, so the blue one are from the class 1 and the red one are from class 2. And now we want to assign the label to the test example. So what should we do? For nearest, we look for its nearest neighbor and assign the assign the category of the test example to the class of its nearest neighbor. Okay, so the concept is quite simple. It's quite simple. So as long as we have training data, we can do nearest neighbor. So does it require any training? This classifier, nearest neighbor classifier, does it require training? Doesn't require any training. Okay. So this is it's also called a lazy classifier. No training is necessary for nearest neighbor classifier. But I think we are talking about K nearest neighbor. So what is K nearest neighbor classifier? For example, X here, X represent text example, X. Okay. Let's consider 5 nearest neighbor classifier. So as the name indicates, we should look for its 5 nearest neighbors. Okay. So for the test sample X, we look for its 5 nearest neighbor. Its 5 nearest neighbors are within this circle. And how should we assign the label to this test sample? What is the how would you classify X in this case? So within this circle, so among its 5 nearest neighbors, 2 are from the red class and 3 are from the black class. So normally we should assign X to the black class using majority vote. Okay. Well, you can also modify the algorithm to using weighted nearest neighbor. For example, we can consider the distance between X, and we can weight their voting based on their proximity, based on their affinity with X. Well, in this case, there are only 2 classes. Okay, what if we have 3 classes, and among its 5 nearest neighbors, 2 from class 1, and another 2 from class, let's say 2 from class A, and another 2 from class B, and 1 from class C. In this case, how would you do the voting? How would you assign the label? Well, this is what we call a tight situation. So class A and B are tied in this case. Okay, so we either are using, we can use weighted voting by considering the distance of the distance between the neighbors and X. Okay, we can use weighted voting, or we can assign the point S to both classes. Okay. So the k-nearest neighbor classifier is the simplest classifier, and we can apply it for image classification. For example, this is a famous CIFAR 10 dataset, and it contains 10 classes, and these are the 10 classes in this dataset. For each class, they are 1,000 test images and 5,000 training images for each class. For example, for the airplane class, you can see each image, the images are quite small. If I remember it correctly, their dimension is 32 by 32. I'm not sure it's 32 by 32 or 28 by 28. It should be 32 by 32. Okay, it's very small images. Okay, and let's apply nearest neighbor to classify the images. For example, we are given these test images. Okay, and how to apply the k-nearest neighbor algorithm for classification. We have these test images, right? We have 10 classes. We have 10 classes. We have these training images. Because the k-nearest neighbor algorithm, it doesn't require any training. So we can, given a test image, for example, this aeroplane, given this test image, we can, how can we do classification? You know, we have 5,000 training images. Given one test image, how can we look for its nearest neighbors? How to identify the nearest neighbors for the test image? Any idea? So each image is 32 by 32. Okay, and we can flatten this image into a vector. And what's the dimension of this vector? It's like 900. Around. I'm not sure. What's this number? 64. Okay, 1024 dimension vector. Okay, so for each image, we can flatten this image and we can represent this image as a 1,024 dimension feature vector. Okay, and then we can compute the distance, Euclidean distance between the text image and each training image. Okay, because the image is quite small, 32 by 32. Normally we do not apply the feature detection algorithm on the image because we can directly use its pixels because it's very small. the pixels to represent this image. So apply nearest neighbor classifier. To apply nearest neighbor classifier, we should calculate the distance between the text image and each training image, because we want to identify its nearest neighbor, right? So what distance function should we use? There are some choices. We can use either L2 or L1. Oh, this is histogram. Sorry. Well, this is for comparing histograms. That's when you calculating. I mean, that's for visual bag of words feature, because you represent each image using histograms. Okay, and if you represent image using histograms, and these are the distance function you may use. Okay, but what if we represent an image using Euclidean using vectors? Then we can apply L2 distance, Euclidean distance, to calculating their distance. We can apply L1 or L2 distance or Manhattan distance, which are not shown on the slides, okay, to calculate their distance. So the selection of the distance function is one hyperparameter for the k-nearest neighbor algorithm. The distance function, okay? Why the distance function is critical, is a key parameter. For example, if we use the L2 distance, if we apply L2 distance or equivalently Euclidean distance on pixels, for the CIFAR image, their pixel representation is a 1024 vector. Okay. So this is an example showing that the L2 distance or Euclidean distance is not a good distance metric on pixels. So we should never use them. Why? For example, this is an input image. This is the original image. And if we mask, for example, the eye region and the region of the mouse to create an occluded image. This is an occluded image. And this image is the shifted version of the original image, only shifted by 1 pixel. While this one is the tinted version. The tone, the color tone of the image has been modified. Okay. So surprisingly, all the three images, they have the same pixel distance to the original image. What do we mean by pixel distance? For example, we just flatten the image to the 1024 vector. We represent each image as a vector using their pixel value. Okay, and then we calculate their pairwise distance. We calculate the distance between the original image and the modified image, the Euclidean distance, because each image is represented by as a vector. So we can calculate their L2 distance. The L2 distance is called the pixel distance here. Okay, so the original image is represented by a vector, and so is the modified image. And for each, we can calculate the distance between the original image and the revised image, L2 distance or Euclidean distance between the two vectors. And surprisingly, each these images, they have the same Euclidean distance with the original image. Why is this bad? Why is this bad? Why it's bad that they all have the same Euclidean distance or pixel distance to the input image? Why the pixel distance or the L2 distance is not an informative distance metric? So among the three modified image, which one do you think is the most similar or the most similar to the original one? The second one, right? The shifted version. So this one, there's barely there's any difference from the original one. So it reserves basically all the features within the original image. Okay, so it should be the most similar to the original one. However, under this distance matrix, you cannot differentiate the three of them because they all have the same distance. Okay, so the L2 distance or Euclidean distance is not an informative distance metric because it cannot describe the capture the similarity, cannot tell. It's not informative about how similar the two images are. Okay, and back to our CIFAR10 dataset. So we can calculate the nearest the pixel distance, Euclidean distance, the pixel distance between the test image and training images. Do we need to examine all the training images to identify the nearest neighbors? Do we need to calculate the distance between the test image and each training image? Which means to identify the nearest neighbors, we need to calculate at least 50,000 distance. Should we do that? Is it necessary? Is it necessary to calculate, to consider all the training images? Is it necessary to consider all the training images when you do nearest neighbor classification? Is it necessary? If you do not have any prior knowledge about the data set, yes, you need to calculate, you need to consider every single pair, every pair. You need to consider every training image because you do not know, because we do not know which images are closer to the test sample. Therefore, for the nearest neighbor classifier, although it doesn't require any training, it's very time consuming during the test phase. Clear? In order to identify the nearest neighbor, you should consider all the training samples within the data set. Let's assume you do not have any prior knowledge about the data set. You need to consider every training image. And let's take a look at the results. These are the nearest neighbors ranked by their pixel distance. Ranked by the pixel distance. And the red one, the one with the red boundary, red box, means wrong classification, which means the nearest one, the nearest sample do not belong to the same category of the identify the nearest neighbor doesn't have the same category as the test sample. Okay? Well, the test sample here is a plane image. It's a plane image, but the nearest neighbor, the pixel distance, but the image with the closest pixel distance, this one. This one is a bird image. This one is a bird image. And also, these are wrong classifications. For example, this is a frog image, but the nearest one is a cat image. Okay? And the reason is due to that the distance metric on pixels is not informative. We do not extract their features, but only use pixels as the feature representation, but the pixel distance is not informative. Okay? And this is the result for nearest neighbor. But remember when we say there's another parameter, hyperparameter in K and N. K is the hyperparameter. Okay? So shall we use nearest neighbor or K nearest neighbor? If we apply K nearest neighbor, how can we choose the, how should we set K? Should I use 5? Should we use 5 or 10 or 20? So this is so this graph shows the accuracy, classification accuracy with respect to different K. With respect to different K. And it seems K, when K being 7, it's around here. It achieves the highest result when K being 7. Okay, so in the following, we are going to introduce why different K, why the selection of K matters, and how to select the appropriate K for your applications. Okay, so this is a picture showing the results of one nearest neighbor classifier. the colored boundary, the boundary of the color region represents the classification boundary. The classification boundary. Okay, so on this image, we have 5 classes. 5 classes. The red one, the blue one, the purple one, the green one, and the yellow one. Okay. And these points, these color points represent training data. So how many training samples do we have for the yellow class? How many training samples for the yellow class? How many training samples do we have for the yellow class? So there are 6 here, 1 over there. So there are 7 training samples for the yellow class. And for the red one, like more than 10. And a few here, about 10. Okay, so the points, the colored points represent training samples. Then what about the boundaries? How can we obtain those boundaries? What do the boundaries represent? The nearest neighbor, one nearest neighbor. You know, given those training data points, given those, we have this a few dozen training data points. For every single for any point on the plan, for any point on the plan, we can apply nearest neighbor algorithm to classify this point, right? For example, this point, we can apply nearest neighbor algorithm to classify this point. So this point will be classified as purple class because its nearest neighbor. Its nearest neighbor belongs to the purple class. And similarly, the point here, this point, will be classified as the green class because its nearest neighbor belongs to the green class. Okay, so the region, the color regions, they are correspond to the classification results for all the points on this 2D plan. Okay, that represents the classification results for all the points on this 2D plan. Okay, so with this classification boundary, for the point here, this point, if this point falls within the blue boundary, we know its category should be blue. Okay, so this boundary, they represent classification boundary. Classification boundary calculated using one nearest neighbor. Clear? Classification boundary calculating using one nearest neighbor. Are those boundaries smooth? Apparently, no. Okay, you can see this boundary. The boundary it's not smooth. And there's even an outlier here. This one. The yellow point sitting inside a cloud of the green points. Okay, so this is the classification results of one nearest neighbor. So due to the outlier, this outlier point, this region, this region is supposed to be the green class. Why? Because this region is inside inside many green points. So this region is supposed to be belong to the green class. However, due to the existence of this yellow point, they are classified. The points within this region, they are classified as the yellow class. Okay, so this shows some limitations about the one nearest neighbor classifier. Then what about the what if we use, okay, this is L2 distance, L1 distance. When we say earlier, if we have this represent image in the form of vectors, we can calculate their L2 or Euclidean distance, or L1 or Manhattan distance. Okay, it's quite simple. We just for L1 we just subtract the two vectors and take their absolute value. The absolute value, and for the L1 you just aggregate their absolute values, and for L2 you should do this. Okay, and what if we use K 3 nearest neighbor and 5 nearest neighbor? Can you see the difference? Well, immediately, let's look at this area. You can see, if you use 3 or 5 nearest neighbors, it smooths out the outlier. Okay, so these regions, they are all classified as the green class. They all classified as the green class, except for the outlier point, because the outlier point come with the label as the yellow class, the original label. Okay, so immediately we can see that if we use larger K, it smooths the outlier. Okay, and also let's observe the de Siron boundary. The de Siron boundary when K being 3, and the de Siron boundary when K being 1, and the de Siron boundary when K being 5. What can you observe on the change? So the de Siron boundary change from complicated de Siron boundary to simpler and smoother de Siron boundary. Because when you use larger K, it brings the effect of smoothing due to the majority voting. It smooths out the outlier. It also smooths out the de Siron boundary. You know, these points. Look at these points here. Okay. So the green, this one could be an outlier because it's close to this one could be an outlier because it should be belong to the it's close to the red points. close to many reference, so you should belong to the red one. Okay, so when you use larger K, it smooths out the outliers. And it makes the decision boundary smoother and simpler. Then what about the wide region? What about this wide, what about this wide region? What do them represent? The wide region. They represent the cases when the majority votes are tied for two classes, for at least two classes. Okay, because we have five, so the votings are tied. Okay, we couldn't decide which class to assign because the votings are tied. Okay, so you can go to this website and try. There's a demo there. You can try the k-nearest neighbor classifier by yourself. Okay. So we're gonna summarize. Gonna summarize using this comparison. A comparison between nearest neighbor classifier and the 5 nearest neighbor classifier. First of all, we can observe the decision boundaries are smoother and the outliers are smoothed out using 5 nearest neighbor classifier. So why nearest neighbor classifier is, what are the limitations of one nearest neighbor classifier? So from our comparison, we know that it's sensitive to outliers because it's one nearest neighbor. It doesn't have the ability to filter out or smooth out outliers because it relies on only one nearest neighbor to make the decision. Okay, and if you make decision based on multiple input, multiple nearest neighbors, you can make more informative decisions. So your algorithm will be robust to outliers. So that being said, the nearest neighbor classifier is sensitive to outliers and also overfits the training data. When we say overfit the training data, when we say an algorithm overfits the training data, you can think of it as the training data. The algorithm memorize anything, memorize everything, including the noisy samples, because it doesn't have the ability to deal with the noisy samples, and you memorize the every input in the training data, which is often noisy, and leading to the decision boundaries, very complicated decision boundaries, and such decision boundaries will, the decision boundaries, because they are very complicated, and they oftentimes they do not generalize well to test data. The decision boundaries, when they are very complicated, which means they are very sensitive to the data variations. They're very sensitive to data variations. And if your algorithm is very sensitive to data variations, it's very sensitive to the data unseen during training. So you will have large variation. And it doesn't generalize well. Okay. Okay. I think we can make one conclusion now that we should avoid setting k too small, right? When using nearest neighbor classifier. But shall we set k to a large number? K shouldn't be set to too large either. If you set k, for example, to a very large number, you will if we set k to a very large number, it may take into consideration of not nearest neighbors, but it's far away neighbors. And the decision by taking the neighbors that are too far from the test sample is not informative. Okay, because when we apply nearest neighbor classifier, we want to make decisions on their on a small local neighborhood. Okay, so k shouldn't be too large either. So here comes the question: how should we select the appropriate k for your problem, for your application? How to select the how to select k? For the k nearest neighbor algorithm, there are two hyperparameters. I mean, obviously k is one hyperparameter, and the other hyperparameter could be the distance function. Okay, k or distance function. How to choose k? So in the following, we are going to introduce the fundamental evaluation pipeline for machine learning, for model training in machine learning. How to choose the hyperparameters. Okay. You know, when we are given a set of training samples, we're given a set of training samples. Usually, you know, here's what we do. Usually, we divide the training set into, for example, 8, 1, 1. 80% of the training set is used for training. 10% hold out for validation, and 10% for testing. You know, all these data, all these examples, they come with labels. We know they are ground truth. Okay? Why do we want to reserve a set of test data? Well, one thing you should keep in mind is that we divide the data set in this way. The test data is reserved for an unbiased estimation. Unbiased estimation of your trained model. What does it mean? The test data should not be used in training. You should not use any test data for training or validation. You treat the test data as you never seen them. Okay, as new data. Because when we train a machine learning model, when we train a machine learning model, we want to understand, we want to estimate its performance on unseen new data. Okay, so we need to reserve a test set. The test set comes with ground truth label. We want to reserve a small set of data to make estimation, unbiased estimation on the performance of our model. Okay, if we use the test data for training or validation, then the evaluation on the test data will not be unbiased. It will be biased because it's involved during training. Okay, so that's the whole idea. We want to reserve a small set of test data which has never been used, has never encountered during the training process. Okay, so that's one key concept. Another one is we further hold out a validation set. The purpose of the validation set is for us to choose the hyperparameters, for us to choose the implementation choices, such as which k to use, which distance function to use in the k-nearest neighbor algorithm. So we are going to use the validation set to compare this k being 1, k being 2, and k being 3, and whether to use L1 or L2 distance. We are going to use this data, the so-called validation data, to compare these design choices. That's our purpose. That's why we need a separate validation set. The test set should never, ever be used in training or validation. Okay? And a separate holdout set, the validation set, is reserved for comparing the hyperparameters and select the best ones. Okay, now let's take another 10 minutes break. Okay. So let's continue to talk about how to choose the best hyperparameters for your model. We need a validation set. So the idea is to split your data into train, validation, and test. So we have explained the reason for doing so. Reserve a test data, a set of test data for unbiased estimation. When we say unbiased, we mean the test data, we have never seen the test data. The test data is never used for training or other validation purpose. Okay? In order to choose the hyperparameters, we need a validation set. So we meaning that we use the training set to train our model, and we evaluate. We use the training set to train our model. Of course, we can our model we can choose different hyperparameters for our model. So for each selection, for each set of hyperparameters, we train a model. For each configuration, for each hyperparameter configuration, we train a model, like model 1, model 2, model 2. And then we evaluate model 1, model 2, model 3. So each correspond to a configuration, a different hyperparameter configuration. Then we evaluate model 1, model 2, model 3 on the validation set to compare which hyperparameter configuration is better. Okay? If the second configuration, model 2, achieve the best result, then we follow this configuration. We choose this model. And if you choose this model, we can use the, for example, we can combine the training set and validation set together to retrain the model using this configuration. And finally, when everything is done, when we complete the training, we can test the trained model on the test set. Okay? Why the idea tool is bad? It is bad. Why shouldn't we use the test data for validation? I mean, why shouldn't we use test data for selecting hyperparameters? If you use test data for hyperparameter selection, you may train your model to fit the test data, and you will never know how your model perform on new data, because you don't have other training data left for evaluation. You have used up all the training data, and you use test data for training. Okay, so you will overfit the test data, and the performance of your model on the test data doesn't represent its performance on unseen data. And normally, if you do so, the performance of your model on test data is usually higher than its actual performance on new data, because you use test data to select the hyperparameters. Okay, and their performance on test data doesn't represent the unbiased estimation of your model. Okay, so the best practice is to use validation set for selecting hyperparameters and to do the training. And when everything is completed, you test the performance of model on the test data. Do not peek at the test set when iterating the two steps. But now I want to mention there's a term called, well, idea 4. It's called course validation. Well, this idea is slightly different from, well, if we say this validation. This is a validation set. Well, cross validation is like this. So we split the data into different folds, and we use the first fold for training, and then use fold 5 for validation. We can iterate this process, and at each iteration, we use a different fold. We use a different fold for validation, and the rest of them for training. Okay, so we can repeat this process until we have used up all the training data for validation. Why do we want to do that? Using different fold of data for validation and the rest of them for training. You know, if we do this, we only need to, we train the model with fixed training data. The training set is fixed. This training data is fixed. But if you do cross validation, well, the training set is fixed. The validation set is also fixed. But if you do cross validation, you need to train the model for different runs. Okay, using different folds of data for training, and a different fold of data for validation. What are the benefits of cross validation? Why do we want to do that? Well, previously we only need to do one round, but now we need to train the model for different rounds, for 5 rounds. If you do 5-fold, if you do 5-fold cross validation, you need to train the model for 5 rounds. Okay. Well, take this training set as example. If we do 3-fold validation, which means we split the training set into 3 folds, and 2 for training, 1 for validation. Okay, so the first 2 for train, the third for validation, or first and third for training, and this for validation, or the second and the third for training and the first for validation. This is a 3-fold validation. Okay, and model 1, model 2, model 3 means what? Well, in terms of hyperparameters, model 1 could be, for example, k being 1. Sorry, k. Let's say k being 5. Okay, k being 5, and model 2 could be nearest neighbor k being 6, and model 3 correspond to k being 7. Okay, and for each model, we use for this run, the first 2 fold are used for training, and the last one used for validation. Then we can compute an error rate in this case, right? And similarly, for the second round, we can also compute an error rate by using the first and the third fold for training and the second fold for validation. Validation means testing. Okay, testing. Then these are test samples. Then we can compute another error rate. And similarly, if you use the second and the third fold for training, and this one for validation, you can compute another error rate on this data on the validation set. The error rate is computed on the validation set. Okay, the error rate is computed on the validation set. Okay, now for k being 5, we have compute 3 error rates using different fold of validation sets and different fold of training data. Okay, and similarly for k being 6, we have compute this. Okay, now we can take the average of the 3 rounds. Take the average of the 3 rounds and identify the best model. Clearly, the best model is K-bin5 because it achieves the lowest error rate. The lowest error rate. Okay, then this is our best hyperparameters. Okay, so initially we split the data into training and testing. Well, the training data include contain the validation data. Okay, data set. The validation data is included in the training data. And then we do cross validation in the following way, cross validation. And we select the best model. The best model, the best parameter here correspond to K-bin5. Okay, K-bin5. And now we can, we have set K-bin5. Now we can use all the data to retrain our model. But for nearest neighbor, it doesn't require any training. Then we can just use all the training data as our training data with K-bin5. And then we test 5 nearest neighbor on the test data. And this will be our unbiased estimation of the performance of 5 nearest neighbor classifier. Okay, well, of course, for the K nearest neighbor classifier, it doesn't require any training. But if you use SVM or perception or decision tree, you need to train a classifier using training data. Okay. Now, let's consider the question we mentioned earlier. What are the benefits of cross-validation? You know, we need to train the model, for 3 rounds using different training set. So it looks like it's very time consuming. So you need to train 3 models for 3-fold validation. Can you think of one advantage of cross validation? Compared to the standard practice. Well, in cross validation, well, in this standard practice, if we 80%, 10%, 10%, well, you do not get to use this 10% data for training, right? I mean, in this setup, if you follow this protocol, this data is only, the validation set is only used for validation. You don't get to use this portion of data for training. But for cross validation, you use up all the data for training. And more importantly, the validation set, the whole out data. In this practice, our training and validation is depends on a random split of training and validation. This is a random split. So if you are unlucky, so this data, this set of data may not be representative enough for your model selection. Okay, may not be representative enough. You may so that's why we can iterate through the training set and evaluate our model using all the available training data. So we can select the hyperparameters. So we can select more robust hyperparameters. Okay, so that's the reason of using cross validation to make the hyperparameter selection more robust and to better utilize the training set. Okay, for the CIFAR-10 case, you can see so this on this graph, it shows the result of K from 1 to 1, from 1 range to 100. And the average results, the result is average over fivefold. Because for each K, we do fivefold cross validation. So the result is average over 5 times. And this represents the variance of the 5 rounds. The variance of the 5 rounds. Okay. So the best performance is achieved when K approximately equal to 7, around 7 for this data. So that's how we choose for hyperparameters. And normally, we do not use cross validation too frequently for deep learning. Why? Because it's too time consuming. You don't want to train your model for many rounds. Okay. Okay. So we're gonna introduce one last classifier for the classic pipeline, and this is the linear classifier. So this classifier is called perceptron. Okay, and you may have heard multi-layer perceptron. So multi-layer perceptron is a network, represent a type of neural network like this. Okay, multi-layer perceptron, where each neuron in the network is a generalization of the perceptron. Each neuron is a generalization of the perceptron algorithm. Okay, so that's why we want to start from the perceptron algorithm. The perceptron algorithm is essentially a linear classifier. Next. It's a step function. This is a sum function. So the sum function, the result of sum function could be +1, -1. Okay, the sum function. This one. Okay, could be a step function. And inside the sum function, this is a linear function. So W is the input. What are the parameters of this function? Oh, sorry, X is the input. X is the input. The parameter of this function is W and B. Well, you can think of one-dimensional case. One-dimensional case, W corresponds to the slope of the classifier, and B corresponds to the intercept of the classifier. Okay, that's for one-dimensional case. But in high dimensional, you can think of X as an image. In the CIFAR-10 case, X is a 32 by 32 image. And if you flatten the image into a vector, then X is a 124 dimensional vector. Okay, so X could be a high dimensional vector because when it represents an image, and correspondingly, W will also be high dimensional. W will also be 1024 high dimensional because this is inner product. Okay, X is a vector, so W is the parameter of the hyperplane, the normal parameter of the hyperplane. And B is a scalar. Okay, so this is a perception classifier. Then what is support vector machine? Support vector machine is also a linear classifier, but different from perception. You know, in this case, the hyperplane that perfectly separate the two classes. There are many such hyperplanes that can perfectly separate the two classes. Okay? Okay, to separate the classes, so this can also perfectly separate the two classes. So is this one. So there are many hyperplanes can separate the two classes. The support vector machine is to choose the best hyperplane. The hyperplane that what do we mean the best hyperplane? The best hyperplane means the hyperplane that generalize the best on test data. So for example, given the two classes, this one is the best hyperplane. This one is the best hyperplane. So the green one is better. The green one is better than the blue one. It's also better than the red one. Okay, why the green one is better? We will not go into detail. Okay, because the green one maximizes the margin between the positive and the negative examples. Okay, it maximizes the margin. The margin is defined as the closest distance, the minimum distance between the supporting vectors and the hyperplane, the minimum. So it's a mass mean problem. So mass mean. Anyway, we won't go into details. Well, intuitively, you can think of this one. This one is intuitively you can understand it as you see the yellow one. This is the best hyperplane because the distance between the supporting vector, this supporting vector is maximized. So it's likely to generalize well on test data. Okay, so I won't go into details. Like I said, we want to understand linear classifier because it's closely related to neural network. Each neuron in neural network is basically a generalization. So it's basically an activation of linear classifier. Okay. Here we have an image because it has 3 channels. So RGB image. So the number of pixels is 3072, meaning that the dimension of X is this. This is a 3072 dimensional vector. Well, here, the W here, it actually contains 10 classifiers. 10 classifiers. Because each row of W is 3072 dimension. Okay, each row of W, because we this is inner product. Okay, inner product. So we can write out W as, W1 transpose, W2 transpose, and W10 transpose. Okay, and X is the this vector. So if you multiply them, what you get is W1 transpose X, W2 transpose X, and W10 transpose X. W1 transpose X is equal to the inner product between W1 and X. Okay? So essentially, W here is a 10 by 3072 matrix, and each row corresponds to a hyperplane. Each row corresponds to a hyperplane. Okay? So if you make the prediction using W, you will, and B here is also a 10-dimensional vector. So if you make prediction using this, it will output 10 number for each class. For the 10 classes, 1 number for each class. Okay? Okay? If we only have 3 class, cat, dog, and sheep, then W is 3 times 3 dimension, 3 rows, 3 times and suppose for illustration purpose, suppose our image is a 2 by 2 image, okay, and we flatten the image into 4 by 1 vector. This is 4 by 1 vector, okay, and now we have 3 by 4. The dimension of W, the size of W is 3 by 4. And each row of W corresponds to a hyperplane. So this is the parameter. So each row of W, the first row of W corresponds to the cat classifier. So this one and this one is a hyperplane for classified cat. And the second one, the purple parameters is the hyperplane for classified dog. And the green one is for the classification of sheep. Okay. And clearly, this image is assigned to the dog class because it's achieved the highest score. And it's wrong, but this is just for illustration. Okay. Okay. And as we said, each set of parameters correspond to classifiers for different classes. This is the first one is cat, dog, and sheep. And the following, these are the visualization. This is the visualization of the corresponding classifier, W, learned for each class. Okay, for example, for the plant class, the learned W, for the plant class, for the plant class. So remember, we say W1, W2, W10, okay? And we can visualize each W. So W1 corresponds to the plant class. So we can visualize W1. This is W1. We can visualize W1 by reorganize W1 into a image, 32 by 32 image. And you can see the learned W1 is looks like a plan. It looks like a plan image. And this is the learned classifier for the cat category. This is W4. And W4 can see the shape of the cat in W4. And similarly, you can see the shape of frog in W7. Okay. Why so? Because when you do the classifier, you are actually compute the inner product. For example, of W7, if you want to classify frog, you are compute the inner product of W7 and the image. Okay, so W7 should look like X. If you consider W7 as a vector in the space, if you the inner product achieves maximum when W7 points to the same direction with X. If they point to the same direction, then this inner product, this score, will be the highest. That is why if you W7 should look like X, should be similar. W7, the hyperplan, the weight, W7, the frog classifier should be similar to frog images. Okay. It should be similar to the frog images because they have the same they point to the same direction, and they have the inner product between them will be the will be large. Okay. So so this graph shows, well, this hyperplan, this is this could be W1 correspond to the airplane classifier, and this one car classifier, car W2. Okay, W2 correspond to car classifier, and this hyperplan, it correspond to, this should be W5 correspond to deer classifier. Okay, so that's how we interpreting the linear classifier, and they look like the images of the corresponding categories. But of course, linear classifiers have their limitations because they can, because they are linear. So linear classifiers are linear, so they won't be able to classify nonlinear data with nonlinear structures. Does that make sense? For example, if you have two classes, blue class and the red class, if you have data distributed in this way, can you learn a classifier to classify to separate the blue class from the red class? Can you separate the blue class from the red one using a linear classifier? And similarly for this data, can you do so? So that's the fundamental limitation of linear classifier. Okay? It cannot handle complex nonlinear structure. So now we have finished the so we have finished introducing the classical statistical learning pipeline, and we have introduced the nearest neighbor and linear classifiers. Comparing nearest neighbor classifier with linear classifiers, the nearest neighbor classifier doesn't require any training, so it's very simple to implement. It's non-parametric. What do we mean non-parametric? Because this classifier, unlike linear classifier is parametric because you need to train W and B. But for the K nearest neighbor classifier, it doesn't have any parameter. Instead, it does has a hyperparameter K. This is hyperparameter, but the model itself doesn't contain any parameter. Unlike the linear classifier, the linear classifier contain W and B, and they need to be trained. Okay, the nearest neighbor classifier doesn't contain, it's non-parametric. So it's very slow at the test time. Why? Because it needs to compute the distance between the test sample and every single training sample to identify the nearest neighbor. Okay, so it's very time consuming, it's very slow at the test time. On the contrary, linear classifier requires training. But once the classifier has been trained, it's very fast at the test time. Because you can just plug in X, the test example, and you will obtain the results immediately. It doesn't require the comparison with every single training samples. Okay, but we have shown that there are fundamental limitations with linear classifier. So that's why we want to introduce more complex classifiers that involve the deep recognition pipeline. And within this deep recognition pipeline, each layer is composed of multiple neurons. And each neuron is actually an extension of a linear classifier. It's just an activation of linear classifier using some ReLU function. Okay, well, here's a brief history of neural network. And as you can see, all those techniques, the XOR function, multi-layer perception, has already been developed decades before the deep learning era. So how to train a neural network, the LSTM, all these techniques already exist decades ago. Multi-layer perception, backpropagation, okay? But due to the restriction or limitation of insufficient compute, we do not have the GPU spectrum, and also we do not have large-scale data to train the network. So these algorithms cannot achieve their potential at that time. Okay, but when we enter the 21st century with more data and with more compute, and these are series of events, these milestone events, the neural networks we have uncovered the potential of neural networks So so the following few images are generated by you know, the neural the diffusion models, generative models, and the multimodal LMs. Okay. So I believe everyone have seen the Sora video. Okay, how this the Gen AI model, diffusion model, can generate videos based on a short description, based on text inputs. Okay. Well, so we're approaching the end of this class, and I want to give you an example of this very popular song. So,
谁说的理想要像模像样？满嘴的口号听起来真响亮，麦克风当武器在嘴角开枪，可现实一巴掌就打得人发慌。你说要为人民去闯，结果开会只剩嘴巴在忙，正义的外衣皱成一团，还敢讲理想？本来应该从从容容，有怨有余，现在是匆匆忙忙，连滚带爬，睁眼说瞎话，你在哽咽什么啦？你在哭什么？哭没出息。
okay, so I think this is a very nice example of showing how Gen AI can be used to generate music and their visual content. So according to the author, so the visuals of this well, these images and visuals are generated. They're not real. But of course, when you generate the image, you should condition on this person. Okay. So you can use the Gen AI tools condition and you supply some image of this person to the Gen AI tools, and you can generate, well, images that fit your narratives. Okay, when the person is yelling or well, fitting your narrative of the your content. Okay, anyway, I think this is a very nice example, and this is a very popular song recently. So the music is also AI assisted. The music is also generated by AI using AI tools. Okay, so these are the examples, well, that demonstrating the capabilities of AI models. And you know, surprisingly, the neural
呢個
networks
係你嗌嘅 burger，用 Food Panda。
well, so we don't have time to explain neural network today, but I would like to mention that the algorithm behind the powerful AI models is just it's just a network consists of many neurons. And each neuron is just a linear classifier. Each neuron is a linear classifier activated by a very simple ReLU function. Okay, but together, when these neurons are organized, when you organize them and you put them together, they can achieve different functions. Okay. Well, in diffusion model or the LLMs. So for example, ChatGPT, it contains 175 billion parameters. Each parameter is an edge. Each parameter is an edge. Okay. So the very complex model are made of simple structures. Okay. So simple structures, simple neurons or classifiers, if you put them together, they can realize very complicated functions, including generating images, proving theorems. Okay. So they have really high capacity and unparalleled potential. Okay, so we'll talk about neural networks next time. Okay, so see you next week.